Bonsoir, je remercie tout le monde dans cet auditoire et ceux qui nous ont rejoints en ligne. Je suis ravi de vous voir tous. Good evening. I thank everyone in this auditorium and those who've joined us online. I'm elated to see you all. Aujourd'hui, vous avez pour des raisons mystérieuses accepté de me laisser présenter les résultats que j'ai obtenus de ma recherche au cours de 4 dernières années. Today, you have, for mysterious reasons, agreed to let me showcase the results I've obtained in my research over the past 4 years. Celle-ci n'aurait pas été possible sans la contribution ingénieuse de Stéphane Weiss, Sulav Lahou, connu par beaucoup sous le nom Cryogenics, et Jeremy Holland qui a placé la barre très haut sous ce que le mot patron devait signifier. These would not have been possible without the ingenious contributions of Stéphane Weiss, Sulav Lahou, known to many as Cryogenics, and Jeremy Holland, who has set an unachievable bar for what the word boss ought to mean. Le titre de ma thèse est Quantum Weak Coin Flipping, Where Weakness is a Virtue. À la fin des 4 premiers slides, sa signification devrait déjà être claire. The title of my thesis is Quantum Weak Coin Flipping, Where Weakness is a Virtue. By the end of the first 4 slides, its meaning, I hope, is already clear. Le plan est de donner progressivement des descriptions plus approfondies de mon travail. Je vais commencer par un résumé de 4 slides. The plan is to give progressively deeper descriptions of my work. I'll start with a 4-slide summary. Imaginez que Alice est à Bruxelles et Bob est à Delhi et que les déplacements sont désormais limités. Imagine Alice is in Brussels, Bob is in Delhi and our travel has been restricted. Pour une raison quelconque, ils veulent lancer une pièce en échangeant des messages. For some reason, they want to flip a coin by exchanging messages. Autrement dit, une fois qu'ils ont échangé leurs messages, ils doivent, tous les deux être convaincus que le résultat est face, par exemple. That is, once they have exchanged their messages, they both should be convinced that the outcome is heads, for example. Bob dit c'est facile, je vais lancer une pièce et te dire la réponse. Alice, apparemment convaincue à debout, crie au scandale. C'est pratique, n'est-ce pas? Comment se voit que tu ne me mens pas? Rétorque-t-elle. Bob says, this is easy, I'll flip a coin and tell you the answer. Alice, seemingly convinced at first, cries foul. That is convenient, isn't it? How do I know you're not lying? She retorts. En pratique, supposons que face signifie qu'Alice puisse garder un objet contesté, comme une voiture de luxe, la question de décider qui gardera la voiture ou de manière générale de se mettre d'accord sur un bit aléatoire sans faire confiance à l'autre joueur s'appelle le coin flipping. For concreteness, let us suppose that heads means Alice gets to keep a disputed object, such as a fancy car. The problem of deciding who gets to keep the car, or more generally, agreeing on a random bit without trusting the other player, is called coin flipping. Il n'est pas difficile d'imaginer qu'Alice et Bob veulent tous les deux les voitures. Donc si Alice triche... Oh shoot. I forgot to do the slides. Ok. Il n'est pas difficile d'imaginer qu'Alice et Bob veulent tous les deux les voitures. Donc si Alice triche, elle essaiera de convaincre Bob que le résultat est face, c'est-à-dire que Alice a gagné. De même, si Bob triche, il essaiera de convaincre Alice que le résultat est pile, c'est-à-dire que Bob a gagné. It is not hard to imagine that both Alice and Bob want the car, so if Alice cheats, she will try to convince Bob that the outcome is heads, that is Alice won. Analogously, if Bob cheats, he'll try to convince Alice that the outcome is tails, that is Bob won. Si nous faisons cette hypothèse supplémentaire, alors le problème est appelé weak coin flipping. If we do make this extra assumption, then the problem is termed weak coin flipping. Pourquoi est-ce une hypothèse? Eh bien, il est concevable que Bob a décidé de renoncer complètement au véhicule à essence, mais Alice ne le sait pas. Elle ne veut pas donner de satisfaction à Bob de toute façon. Why is that an assumption? Well, it is conceivable that Bob has decided to forego petrol-burning vehicles altogether, but Alice is unaware of this. She doesn't want to give Bob the satisfaction either ways. Also, to contrast weak coin flipping from coin flipping, we often refer to coin flipping as strong coin flipping. Maintenant que nous avons défini le problème du coin flipping comme étant deux personnes qui échangent des messages pour s'entendre sur un pile ou face au hasard, nous pouvons aller plus loin. Now that we've defined the coin flipping problem as two people who exchange messages to agree on heads or tails at random, we can proceed further. Un schéma qui indique à Alice et Bob comment échanger des messages pour résoudre le problème du coin flipping s'appelle un protocole coin flipping. A scheme that tells Alice and Bob how to exchange messages to solve the coin flipping problem is called a coin flipping protocol. Mais évidemment, différents protocoles offriront différents niveaux de sécurité. Rappelez-vous le protocole proposé par Bob où il lance une pièce et déclare le résultat. C'était un mauvais protocole. But obviously, different protocols will offer different levels of security. Remember the protocol proposed by Bob where he flips a coin and declares the outcome. That was a bad protocol. Le facteur de mérite d'un protocole coin flipping est donné par un nombre epsilon qui est connu comme le biais du protocole. The figure of merit of a coin flipping protocol is given by a number epsilon, which is known as the bias of the protocol. Il capture à quel point une personne qui triche peut biaiser le résultat vers la valeur souhaitée. Ainsi, un 0 signifie que le protocole est complètement non sécurisé. Un 0 signifie que le protocole est sécurisé et un demi signifie qu'il est complètement non sécurisé. Pourquoi un demi? Nous verrons plus tard. It captures how much a cheating player can bias the outcome towards their desired value. So a 0 means that the protocol is secure and a half means it is completely insecure. Why half? We'll see later. Considérons tout protocole où des messages classiques sont échangés, c'est-à-dire que le message n'utilise pas de quantique pour mettre en œuvre le coin flipping. Consider any protocol where classical messages are exchanged, that is, the messages don't use any quantum to implement coin flipping. Il a été démontré que tous ces protocoles doivent être totalement non sécurisés, c'est-à-dire avoir un biais de moitié. Cela est vrai aussi bien pour les strong et weak coin flipping. It has been shown that all these must be completely insecure, that is, have a bias of half. This is true of both strong and weak coin flipping. Mais que se passe-t-il si les messages sont quantiques? Je vais expliquer en détail ce que signifie un message quantique. Pour l'instant, considérez-les comme des messages qui exploitent certaines propriétés exotiques des atomes et des photons. Dans ce cas, le biais a une histoire plus intéressante. But what happens if the messages are quantum? I will explain in detail what a quantum message means, but for now, think of them as messages that harness some exotic property exhibited by atoms and photons. In this case, the bias has a more interesting story. Pour un strong coin flipping, un génie russe, Alexei Kitaev, a prouvé que le biais doit être borné inférieurement par un nombre fixe qui est d'environ 0,207. Cela signifie qu'il est impossible de faire du strong coin flipping parfaitement ou même presque parfaitement. Le meilleur protocole explicite que nous, en revanche, a un biais de 1 quart. For strong coin flipping, a genius hailing from Russia called Alexei Kitaev proved that the bias must be lower bounded by a fixed number, which is approximately 0.207. This means that perfect or even near perfect strong coin flipping is impossible. The best explicit protocol, on the other hand, has a bias of a quarter. En ce qui concerne le weak coin flipping, Motion a annoncé un résultat révolutionnaire en 2007 en s'appuyant sur les travaux de Kitaev. Il a montré qu'il existe bel et bien des protocoles de weak coin flipping avec un biais qui disparaît. La flèche à côté de epsilon indique que le biais peut approcher de 0. Indique que le biais peut approcher de 0 autant qu'on le souhaite. Cependant, ce preuve n'est pas constructive. Cela signifie que Motion savait qu'un protocole existait, mais qu'il ne savait tout simplement pas de quoi il s'agissait. As for weak coin flipping, by building upon the work of Kitaev, Motion announced a breakthrough result in 2007. He showed that weak coin flipping protocols with vanishing bias really do exist. The arrow next to epsilon indicates that the bias can be made as close to 0 as one wishes. However, his proof was non-constructive. This means that Motion knew a protocol existed, but he just didn't know what it is. Le meilleur protocole explicite connu pour le weak coin flipping a un biais de 1/6, également dû à Motion. The best known explicit protocol for weak coin flipping has a bias of 1/6, also due to Motion. Fun fact, after his breakthrough result, he left academia. And this has happened to 2 other researchers who made significant contributions to the subject. I hope this trend doesn't possess any predictive power over the fate of current researchers. Yes, my standards for the word fun aren't quite as high. Coin flipping can do this to you. Donc, comme vous l'avez peut-être deviné, notre contribution a consisté à combler cette lacune. Nous avons élaboré des protocoles de weak coin flipping qui approchent le biais zéro. Ceci complété m'ont aperçu en 4 slides de nos contributions à ce sujet au cours de 4 dernières années. So as you might have guessed, our contribution was to close this gap. We constructed weak coin flipping protocols that approach zero bias. This completes my 4-slide overview of our contributions to this subject over the last 4 years. I hope everything so far has been clear. In this section, I intend to give you a rather visual and conceptual introduction to quantum mechanics. Many insights can be conveyed without using any equations, which is precisely what I've tried doing here. I will also tell you how this relates to the exciting fields of computer science and cryptography by discussing simple and intuitive examples. In the interest of time, henceforth I'll restrict myself to English only. I must, however, thank Zach and Celia for their assiduous support with the French translation. So we start with a very basic concept, the location of a particle. Suppose we know that a particle is sitting at some location. How might we represent this knowledge? Well, we could measure the distance of this particle from some fixed point represented by q1, as shown in the graph. For simplicity, I assume that the particle can be moved along this line. Can only be moved along this line. What if we did not know the location of the particle with certainty? Suppose we knew that it could either be around the point q1 or it could be around the point q2. How might we represent this knowledge? Well, we could draw a probability distribution as shown. Higher the likelihood, taller the peak. So far, everything I've said is how the world was thought to fundamentally behave, at least as far as particles are concerned. That is, until the 1920s. At this point, numerous ingenious experiments were painstakingly performed and bold new ideas were proposed. Most physicists conceded that nature was telling them even their basic understanding of particles was flawed. The probabilities had to be replaced by what they call probability amplitudes. Probability amplitudes have 2 important properties. First, they can be negative. In fact, they can even be complex numbers for the experts. Second, squaring it yields the probability of that event happening. So this is indicated by the final figure. These 2 may be thought of as the first 2 postulates of quantum mechanics. Let us now extend this understanding to 2 particles. I repeat the same exercise, but with 2 particles this time. Suppose we know that the first particle is sitting at a location Q, and the second particle is sitting at some location P. I can represent this using a single point in a 2D plane as shown. The first axis encodes the position of the first particle, Q, and the second encodes the position of the second particle, P. Let us now switch to the probabilistic case. Suppose I know that the position of the particles are correlated, that is, they are situated at location QP, either they are situated around the location QP or they are situated around the location minus Q minus P. This can be represented by 2 peaks centered at QP and minus QP as shown. And that completes the probabilistic case, like sort of an indication. What about the quantum case? In this case, we can consider, for instance, the hill centered at QP stays positive, while the hill centered at minus Q minus P becomes a valley. The question is, why does all of this matter? So to address this, we first need to simplify things a little bit. So I started with the particle's position, but this is a continuous property. That is, roughly speaking, it can take any value. This makes the description a little bit more cumbersome, that is necessary for our purposes here. Thus, we focus on discrete properties of particles. These can be, for instance, spins, polarizations, energy levels, modes, etc. But do not worry if these do not sound too familiar to you, because we can discretize these things. So for example, we can say a particle on the right hand side of some reference location will be called plus, and the one on the left will be called minus. Energy levels are also easy to understand. An atom's usual state is termed ground state. If we shine a laser on it, for example, it can absorb that energy and jump into an excited state. These levels are discrete. Quantum mechanics' ability to explain this was one of its key triumphs. We represent the ground state as G and the excited state as E. We represent, so those strange symbols that you see with a bar and an angular bracket, these were an invention of a famous physicist, goes by the name Paul Dirac. For us, they simply refer to the state of the system that we are describing, that is, the state of the particle. Now we play the same game. We start with a single particle, or for concreteness, a single atom. If we know that it's precisely in the ground state, we represent this knowledge using the ket G, or the state G. If we know that it is in the ground state G with some probability A, for example, and in the excited state with some probability B, we may represent it using the graph as shown. We may also write it as a probability vector AG plus BE, as is written. Finally, in the quantum case, we use probability amplitudes. Probability amplitudes can be negative. This we represent using the graph, as shown. The associated state may be expressed as alpha G plus beta E, where I'm using Greek symbols to indicate that it's a probability amplitude, so the values can be negative. Now suppose we have two atoms, both in the ground state. We represent this using the states GG. If we knew, for example, that only, let me say it again. If we knew some probability distribution over the states of these atoms, for example, we knew that the atoms of both being in the ground state is the highest, the graph could look something like this. The state is now represented using a probability vector A ground plus B ground excited plus C excited ground plus D excited excited. And here B, for example, encodes the probability of the first atom being in the ground state and the second being in the excited state. Finally, for the quantum case, the probability amplitude can be negative. We represent it using the graph as shown. The state is similarly written, except that we use alpha, beta, gamma, and delta to indicate that they're now allowed to be negative or in general complex. So I hope this makes sense, although I still haven't told you why all of this is relevant. To do this, and to see how these strange laws of nature can be put to use, we consider a simple problem, that of multiplication. And I use this to contrast the functioning of a regular computer, such as your phone, with how a quantum computer might function. So you must have heard that computers internally store all their information as strings of zeros and ones. So suppose we want our computer to multiply the numbers 3 and 3. So we represent this as a circuit that takes as input the numbers 110 and 110, which are the strings corresponding to the number 3. And we want the output to be 10010, which corresponds to the number 9. Now this operation can be performed very quickly on a classical computer. We will not try to make the notion of fast much more precise, and intuitive understanding suffices for our purposes here. How might a quantum computer perform this computation? Well, we store the first input, the number 3, using 3 atoms, excited, excited, and ground. Similarly, the next input, again, the number 3, using 3 atoms as excited, excited, ground. And you can see the excited corresponds to 1 and ground corresponds to 0. Okay. And we could do it the other way, it doesn't matter so long as the states are distinct. Of course, abstractly speaking, experimentally, it might be much more complicated. Finally, we keep 5 atoms in the ground state to hold the result. Recall how when we considered one atom, we had a one-dimensional graph. And when we considered 2 atoms, we had a two-dimensional graph. Now we have 11 atoms, so the graph must really be 11-dimensional. But for illustration, I pretend that this two-dimensional graph represents the 11-dimensional graph corresponding to the 11 atoms. To perform the computation, this probability weight needs to be moved to the state which corresponds to the answer. This may be done by means of physical interactions with the atoms, such as shining lasers on them. The end result must be that almost all the weight is on the state where the atoms that encode the inputs are unchanged, and the atoms that encode the answer are in the state excited, ground, ground, excited, and ground, which essentially corresponds to the encoding 10010, and this in turn corresponds to the number 9, which is the answer. So this operation is also performed very quickly by a quantum computer. And so we don't really see any advantage coming from quantum computers yet. So let's remedy this. Let us consider the opposite problem. That is, suppose that a number is given, say the number 9 again, and we ask what are the numbers whose product yields the number 9. We can again represent it as a circuit that takes as input the number 10010, and the output is supposed to be the numbers 110, 110, which correspond to 3 and 3. Mathematicians have actually struggled with this problem for over 2 millennia, and yet we do not know of any fast algorithm for solving this problem. So you already know where I'm going with this. What happens if we consider a quantum algorithm? So again, we are going to store the information as depicted using atoms. Peter Shaw, a researcher at MIT, found a fast algorithm that can shift a significant part of the weight from this input state onto the state corresponding to the answer, that is the state 3,3, while leaving the input 9 unchanged. The key insight he used was that the weights can be positive and negative during the computation. He used clever techniques for moving these weights around so that they cancel everywhere but accumulate at the right answer. As before, physically this algorithm is implemented by means of interactions with the atoms using lasers, for example. So there you have it. It's quantum mechanics in action. It's solving an ancient problem which was thought to be, which is as far as we know, very difficult for a classical computer despite our best efforts, and is a problem that can be solved very quickly on a quantum computer. And this result was established by Peter Shaw in 1994. Okay, now we move on to cryptography. So one of the most basic tasks one considers in the study of cryptography is the ability of exchanging secret messages. Suppose Alice wants to tell Bob that she's getting bored, but she doesn't want anyone else, such as the speaker, to learn this. She could, for example, send a message over the internet. It is likely that this action behind the scenes uses what is known as the RSA crypto system. The name is not too important, but what is important is that the system relies on the assumption that factoring is a hard problem. But we just saw that a quantum computer can easily factor numbers. Yes, this means that a quantum computer can in fact break the security of some of the crypto systems we are using even today. The catch is that building quantum computers has proved to be notoriously challenging. Although it doesn't mean that we shouldn't take precautions already, because information stored now can potentially be cracked or hacked or decrypted, that's the right word, afterwards. So suppose the message, so that is the situation so far. There is an older, more inconvenient, albeit safe method of exchanging information. It posits that if Alice and Bob meet and agree on a random key, then they can securely communicate afterwards using this key. This is not very hard to see. So suppose the message Alice wants to send is the number 3, and the key that they agreed to was the number 2. The eavesdropper at this point knows neither the message nor the key. Alice encrypts a message by adding it to the key, that is, she adds 3 to 2 to obtain the number 5 and sends it to Bob. Now, even if the eavesdropper learns this number 5, he can't extract the message from it because he doesn't have the key. Bob, on the other hand, can easily decrypt the message by subtracting the key from the encrypted message. That is, subtracting 5 from 3 to obtain the number 2, which is the message Alice had sent. The problem, of course, is that meeting physically is inconvenient. This precise problem was solved by RSA, but we just saw that quantum computers renders the protocol insecure. The solution, as you might have guessed, again comes from quantum mechanics. So in the year 1984, Bennett and Bresser proposed what is called a quantum key distribution protocol, which solves precisely this problem of key distribution without Alice and Bob having to physically meet. The protocol involves the sending of a photon by Alice, as is shown in the diagram. This photon is in one of the 4 states as described. By now, I hope at least the notation makes some sense. Bob performs certain operations on these incoming photons and measures it. The details are not too important here. What is relevant is that the protocol was shown to be secure, granted the laws of quantum mechanics are valid. No further assumptions are needed. Contrast this to the RSA scheme, which relied on the hardness of factoring numbers. This was the famous contribution of quantum mechanics to the field of cryptography, basing the security of a protocol on the laws of physics as opposed to some assumption of difficulty of solving a mathematical problem. Alright, so cryptography today is a rich field and has many branches. We briefly saw the branch of secure communication where Alice wishes to protect her communication with Bob from an eavesdropper. There is another branch called secure two-party computation. Here, Alice is given an input X and Bob is given an input Y. They wish to evaluate a function of both their inputs, but they don't want the other party to learn their input. That is, Alice shouldn't learn X and Bob shouldn't learn Y. Consider a realistic example. Suppose that there are two investment banks and they want to ensure that their risks are non-overlapping. Since these banks compete, they don't want the other bank to learn anything about their investment, while still simultaneously solving the problem that they do not have a large overlap in their investments. Obviously, they don't also want a third party to mediate the process. A simpler, less realistic example is called the millionaire problem, and I'm sorry for the spelling mistake. Two millionaires want to ascertain who is richer, but neither wants the other to learn exactly how much money they possess. Now that I've defined what secure two-party computation is, let me tell you that this was shown to be equivalent to a problem which is simpler, and it's called oblivious transfer. This problem is also called this problem is sort of a cryptographic primitive. In the study of algorithms and cryptographic protocols, it's useful to reduce the problem to a simpler form. This was a breakthrough result at the point when it was found and published. It was then shown that there is something called bit commitment. This is also a cryptographic primitive, and it is known to be weaker than oblivious transfer. That is, one can do bit commitment using oblivious transfer, but not the other way. Quantumly, it was found that bit commitment can in fact be used to do oblivious transfer, but that is as far as the quantum advantage goes, because it was shown that bit commitment itself is also impossible quantumly. What about something weaker? Coin flipping was one such candidate, but we saw that Kitaev showed this is impossible as well. What about weak coin flipping? Well, we already alluded to this. Moshon showed that weak coin flipping is actually possible, but we do not have an explicit protocol for this. So weak coin flipping, it turns out in this hierarchy, is the strongest known primitive, which is possible quantumly, while classically all of these are impossible. So this is where weak coin flipping fits into the larger context of cryptography. I must add that weak coin flipping has been used as a black box to show optimal strong coin flipping, bit commitment, and oblivious transfer, and this makes the study of weak coin flipping even more interesting. I hope I've been able to convey or at least explain to some extent what quantum mechanics is and how it relates to the fields of computer science and cryptography, and finally how my research problem fits into this larger context. The following sections might get slightly technical and are targeted at a scientific audience, and I nonetheless hope that it is clear for somebody who's been following the slides so far. To understand coin flipping slightly better, we begin with exploring the different situations which can arise when we try to analyze the security of it. So we call a player honest. We say that a player is honest if they follow the protocol exactly as described. Now, 4 situations can arise. It could be that Alice and Bob are both honest. In this case, we want the protocol to be such that it yields a heads and tails with equal probability, and that they both agree on the outcome. That is, Alice and Bob both agree that the outcome is heads or tails. When Alice is cheating and Bob is honest, Alice can of course bias the protocol towards her desired value. We want the protocol to be such that it protects the honest player, which is Bob in this case. We can consider the converse scenario where Alice is honest and Bob is cheating. In this case, Bob can bias the outcome towards his desired value, and we want the protocol to be such that it protects Alice from a cheating Bob. And finally, there's the situation where Alice and Bob are both cheating, that is, neither of them is actually following the protocol. and we don't consider this case because it doesn't actually depend on the protocol. They can both be doing arbitrary things. Right. So the bias of a protocol is defined as follows. So consider any protocol that solves the coin flipping problem. We say it has a bias epsilon if neither players can force their desired outcome with probability greater than a half plus epsilon. Okay. Now, to understand this a little bit better, we introduce some notation by specializing to the case of weak coin flipping. Just to quickly remind you, weak coin flipping is the case where the players have opposite and known outcomes. That is, Alice wants heads, for example, and Bob knows this, and Bob wants tails, and Alice also knows this. Okay, so now when Alice and Bob are both honest, the probability that Alice wins is given by the symbol PA, and the probability that Bob wins is given by PB or P sub B. Right. If Alice is cheating and Bob is honest, then the probability that Alice wins is given by P star A. That is, the cheating player winning is P star A. And when Bob is cheating and Alice is honest, the probability that the cheating player, which is Bob in this case, wins is given by P star B. The bias in this case can be expressed using the symbols we've introduced. So the bias becomes the smallest epsilon such that P star A and P star B are both less than half plus epsilon. They're bounded by half plus epsilon. It's easy to see that epsilon is bounded between 0 and half. It is half because the cheating probabilities can be 1. So it has to, epsilon can be at most 1, at most half, so the probabilities. And epsilon cannot be smaller than 0 because a cheating player always has the option of following the honest protocol and winning with probability half. We assume P and PB are half. So that is why the bounds are on epsilon as shown. Okay, so now to get a feeling for these numbers, these symbols, let us consider a simple protocol. So let's consider a protocol where Alice flips a coin and declares the outcome. So now when Alice and Bob both are honest, and assuming that the coin is fair, the probability that Alice wins is half and probability that Bob wins is half. If you don't have a scientific background, it may be a good idea to just pause this and think about the other two cases. I'll proceed anyway. The case when Alice is cheating and Bob is honest, then the probability that Alice wins is given by 1 and that of Bob is 0 because Alice can simply lie and the protocol requires Bob to simply accept whatever Alice says. The other way, however, is going to be the following, that if Alice is honest and Bob is cheating, then the probability that Alice wins is going to just be half because Alice is flipping a fair coin and Bob has no control. The protocol just says that Bob has to accept whatever is the outcome. So he has no say in the outcome of the protocol really. Right, so the bias in this case is the smallest epsilon such that P star A and P star B is less than half plus epsilon, right? And sorry, this was the general definition. When we plug in the value of P star A, P star B, we see that epsilon is a half. For the experts, this might be completely trivial, but it's just good to take an example and work it out. Right. So to study coin flipping, Kitai came up with three magnificent protocols. Three amazing formalisms. Let's not use the word protocols because that's not correct. Right. So the first is called the first formalism is called a protocol. The second is called a time-dependent point game, and the last finally is called a time-independent point game. We'll see what these mean in more detail. The important part is that all of these were shown to be equivalent. In fact, they were shown to be constructively equivalent. That is, given a time-independent point game, for example, you can actually explicitly find the time-dependent point game. This is not hard. However, the last step, that is going from a time-dependent point game to an explicit protocol, was non-constructive, and this has been the focus of my research in these last 4 years. Now let us look at each of these in a little bit more detail. So let's start with the protocol. So in this formalism, and I'm going to assume quantum mechanics to a certain extent from now. So in this formalism, the claim is that any protocol can be cast into the following form. So we suppose any weak coin flipping protocol, can be cast into this form, where Alice has some local registers. We can think of them as atoms. Bob has also some local registers, and then there are some atoms which function as message registers. So Alice interacts her atoms with the message atoms by applying some unitary, and then she sends the message atoms to Bob. Bob applies some unitary U2, which is some physical operation, on the incoming atoms and on the atoms that he locally has. And this process of sending and receiving messages is continued for a while until the very end, where they both make certain measurements. The variables which are involved here are called the usual variables that appear in any quantum mechanical problem, that is the density matrices that define the state, and the unitaries which define the operation. So the protocol is essentially specified by the unitaries and the initial state, of course. Okay, this corresponds to the security of this protocol corresponds to the evaluation of two STPs. So P star A can be cast as an STP in the following sense. So you say that P star A is defined to be the following. You maximize the probability that Bob makes a measurement and concludes towards the end that Alice won, subject to the constraint that Bob follows the protocol exactly, that he applies the unitaries U2, U4 and so on. And you optimize over all the remaining freedom, and this you can cast as an STP. The other is called, there's an analogous program for P star B, where we can maximize over the probability that Alice makes a measurement towards the end and concludes that Bob won, and maximize over all possible cheating strategies for Bob. An STP, for those of you who don't know, may just be, for our purposes here, be thought of as a scheme which is easy to evaluate. So if you can cast a problem as an STP, usually it's easy to evaluate, and it also has some nice properties. In particular, one can use SDP duality to actually find a bound on the protocol, the cheating probabilities of the players, and this can often be done analytically. So this is why this is a very nice formulation. So this was the protocol formalism. Now let's move to the time-dependent point game formalism, and you will see how magnificently simple it becomes. So a time-dependent point game is essentially just a sequence of frames where each frame is supposed to be some points on a plane. And the sequence of frames is as follows, that it must always start with 2 points at the location 0, 1, 1, 0, and they must have equal weight, a half and a half, and they must end at a single point, and we denote the coordinate of this point by beta alpha, and this point should contain all the weights, that is, the weight should be 1. The claim is that if we follow certain rules for moving these points in the intermediate frames, then there exists a protocol such that the cheating probability for Alice is bounded by alpha, the coordinate of the ordinate of the final point, and P star B is bounded by beta, the coordinate of the final point. And why this formulation, where this comes from, has to do with a very nice characterization of operator monotone functions, which I will not have the time to go into, but if you're interested, write to me and we can discuss. Okay, now let me give you, I obviously did not tell you exactly what the rule is, but let me give you some simple rules that can already be applied. So if you have a set of points and you want to go to a single point, then the rule is as follows. The coordinate of this point can be equal to, the coordinate of this point cannot be less than the average coordinate of the initial set of points. Okay, so that is basically the average has to be somehow preserved. The second is a split. So if you have one point and you split into multiple points, in this case the harmonic average location of the final set of points cannot be less than the coordinate of the initial point. Finally, we have the raise, where we increase the coordinate of a point, and this is always allowed. And remember that the coordinate encodes the cheating probabilities of the players, the coordinate of the final point, and so therefore raising points is not something we really want to do. More generally, if we have n points, so 3 points for example, and we send them to 2 points as shown, then they have to satisfy this inequality which I have written, where xgi encode the coordinates of the initial points and pgi encode the weights of the initial points, and similarly for xhi and phi. I must add that we can move points either along a horizontal line or along a vertical line, so they have to be aligned. Right. Now let us try to apply some of these rules to see if we can construct something simple. So okay, I turn on my laser pointer. So suppose we have one point here. So, right, so these are 2 points that we must start with. Any time dependent point game must start like this, Now we want to do something non-trivial with it. So the first thing we could possibly try doing is to raise, for example, so that these 2 points are aligned, and then we can try to merge these 2 points so that we end up with a single point at the location 1.5. And this should remind you of something. This essentially corresponds to the flip and declare protocol that we had, where Alice could cheat with certainty. So this is 1, the y coordinate, and the x coordinate is half, which means that Bob cannot cheat at all. So we applied these simple moves and constructed something trivial. So that's not as interesting. But we did not use the split. If you use the split, it turns out that we can in fact construct something highly non-trivial. At least that is what the case was in 2002. So if you start with a split and then we raise this point at the edge, we merge it with this initial point, and then we merge with the final point, and one can choose the weight so that there's nothing left, right? There's nothing extra, so everything matches. The coordinate of the final point turns out to be 1 by square root 2, 1 by square root 2, and this actually corresponds to a protocol which was found in 2002, and it was published in PRL. So you can see the power of the formalism. It lets you lets you find some results which were published in very high impact journals. And it might be interesting to see that this protocol actually corresponds to the bound on strong coin flipping. So at that point, it wasn't even clear whether weak coin flipping is actually different in any way, or it's just that the proof technique doesn't apply to weak coin flipping. But in this, the way I've presented it, it's conceivable to imagine that maybe if you do more splits, we can do better. Maybe we can even approach 0. Well, we can do better. We can't approach 0 though. So the best that was shown was by Motion, and this actually corresponds to the 1 by 6 bias protocol. And this protocol was called dip dip boom, and the reasons for these, the name, are not quite as clear. Okay, so that was the time dependent point game. Now I will quickly describe a time independent point game and move on to telling you why it is important. So the key idea here is that we allow for negative weights. The negative weights are useful because instead of considering a sequence of frames, it suffices to consider 2 functions. And the functions have to be such that when you add them, they correspond to the final frame minus the initial frame, so that the intermediate points essentially cancel out. And h and v have to satisfy a condition which is very similar to the equation I had written earlier. So it's not very important to get into the details. What is important is something I already mentioned, which is that a time independent point game can be converted to a time dependent point game with essentially the same last frame. Technique that they use is called a catalyst state, which I might have some time to discuss towards the end. Why I mentioned the time independent point game framework is because it is in this framework that Motion showed, or in fact Motion proved his fundamental result that weak coin flipping is actually possible. So what he does is he constructs time independent point games with epsilon equal to 1 by 4k plus 2. And the k here actually corresponds to the number of points along the diagonal in the diagram as shown. As you can see, k is made larger, epsilon tends to 0. For k equal to 1, one recovers the 1 by 6 bias protocols. It can be somehow thought of as a generalization of that particular family of protocols. And the technique that he uses is actually surprisingly quite simple. He just uses some polynomials to construct them. But of course, it takes certain results to be shown, and then it's very interesting. So this completes my introduction to the different frameworks which were introduced for the study of coin flipping. And now I can tell you my contributions. So I would like to basically tell you 4 things that we did, and they're all essentially targeted towards converting a time-dependent point game to an explicit protocol, which was the missing link. So we come up with what we call a time-dependent point game to explicit protocol framework. I know that's very imaginative. This framework is nice because it says that for every frame of the point game, we'll see this in a moment, if one can satisfy a certain condition, if one can find a unitary, that satisfies a certain condition, then one can actually construct the protocol. And this was already known, but the condition was a little bit more complicated. We were able to simplify it. And then we were able to use the simplified condition to convert Motion's point game for k equal to 2, that corresponds to bias 1 by 10, as we saw, into an explicit protocol. And this actually relied on a fairly educated guess. By educated, I mean by doing lots of trials and errors. And we had to use perturbation theory. And the only reason it worked, it was basically because the problem in the end becomes a 2x2 matrix, and this one can actually play with. But going beyond was hard, and Therefore, to find the analytic solutions, we had to use a different approach, which does not use any perturbation theory. One such class of solutions we found using a geometric techniques, which were inspired by the EMA algorithm, which I'll describe in just a moment. The other set of solutions were essentially algebraic, and they were simplified versions of the geometric solution. They were essentially motivated by the geometric solution, and this I will hopefully be able to describe in some detail. The EMA algorithm, okay, I'm sorry, I should have mentioned before talking about the EMA algorithm that the analytic solution here, what I mean by analytic solution is that we found the unitaries that are needed for converting Moshor's point games into explicit protocols, which are needed for TEF, which we'll also see in just a minute. So the analytic solutions are the unitaries, and once we combine them with TEF, we can actually convert Moshor's point games into explicit protocols. However, it's not clear that Moshor's point games are the only point games. Obviously, there may be others. In fact, there's one by Pelchat and Hoyer, and they may not even be optimal in other settings, right? So therefore, there is interest in trying to see if one can convert arbitrary point games into explicit protocols. And towards this end, we came up with what we call the EMA algorithm. This numerically constructs unitaries which are needed for TEF, for converting any point game into an explicit protocol. Okay, so let me describe TEF in a little bit more detail. I'll describe these three things. The 1 by 10 is not as significant in the grand scheme of things. And let's get started. So for TEF, suppose you're given a time-dependent point game and we focus on 2 consecutive frames of the point game. What TEF says is the following, that this step in the point game essentially corresponds to applying some standard unitaries which are in gray and a non-standard unitary which is in black. And the non-standard unitary in black is essentially the one which I've boxed in blue. So the unitary has to satisfy the following. It has to send V to W. So V actually encodes the weights of the points initially, and W encodes the weights of the points finally. G1 to Gn and H1 to Hn are the bases. So if you have 2 points, you have G1, G2, and if you have 2 points afterwards, you have H1, H2. So this is just, they together span an orthonormal basis. So U acting on V basically means that V here is root PGI GI, so it just encodes the probability weights initially. So the initial probability weights have to be mapped to the final probability weight. So that's the first equality constraint. The next is an inequality constraint, and this says that XH, which you can see here, encodes the coordinates of the final point, right? So the coordinates of the final point, and XG encodes the coordinates of the initial points. So the unitary must satisfy this inequality, which encodes the coordinates of the initial and final frame. So if you can find a unitary which satisfies the constraints I've mentioned for every such for every pair of frames, consecutive frames, then we can convert that particular point game into an explicit protocol. So let's look at some simple cases. So the first thing we tried was to see if we can do this for the splits and the merges, because they are essentially the simplest and they actually already correspond to the 1/6 bias protocol. And it turns out that if we have this unitary which just sends W to V and V to W and is identity everywhere else, it does nothing to any of the other states, turns out that this can actually this satisfies the required constraints. And the significance is that this actually lets us control the point game, the 1/6 bias point game, into an explicit protocol. And this, to the best of our knowledge, was not known earlier. We knew the protocol separately and we knew the point game separately, but we did not know how to convert the point game into an explicit protocol. So that completes my quick overview of TEF. Now let's look at the analytic solution, right? Because we know how to do the split, we know how to do the merge, but for converting Moshor's point games, we need the unitaries that are used in these unitaries that are required by TEF, which satisfy the constraint. Turns out that the unitary that I've written here fits the bill, and I just flash it in front of you because I just want to tell you that it can actually fit into a slide, which is interesting because the first article on the subject by Moshor is around like 80 pages, so it's kind of nice to have something which is compact. But we can still get some intuition about what the unitary is doing. So in a certain class of Moshor's move, suppose that n points are going to n points. So in this case, the unitary will do the following. It will send V to W, which it has to. That was the first constraint. The next thing it does is actually quite simple. It basically just multiplies the coordinates xg with the weight V, similarly, and sends it to the analog in the final frame, that is xh multiplied with W, and we remove the components along the previous vectors. And we repeat this with higher powers of the matrices xg and xh. And it turns out that this unitary actually works. It satisfies the required conditions. And the significance of this construction is that this means we can actually convert Motion's point games into explicit protocols, and that means we can achieve vanishing bias. The limitation, of course, is that a priori, as I already mentioned, this only works for Motion's games. So what if we want to go and do something more general, like if we have maybe a more efficient game somehow? So to understand this, we introduced, or to solve this problem, we introduced what we call the EMA algorithm. And I just want you to quickly recall the two conditions. So the unitary had to be such that V is sent to W, which is what Tef said, and XH, and there's the inequality, right? Now this one can simplify, and we'll not see why we can do this, but for the moment just assume that we can drop the projectors. I didn't even mention, so the EH, I'm sorry, I forgot to mention this, the EH were projectors on the H space. It was on the slide, but we can forget about them at this point. And we can in fact consider XH to just be diagonal matrices which encode XH, the final coordinates and the initial coordinates. So we don't even have to worry about a complicated basis, just put it in a simple basis and encode the as diagonal entries. I'm sorry, it's enough to encode the final coordinates, for example, into the diagonal entries of a matrix, and W can just be a vector which encodes the weights as square roots, as I've written, and similarly for V. So it's quite similar to what we did, except that the bases are now somehow simplified. Right, so this I already mentioned. So the nice thing is that if we do this, and if we do some additional things, such as if we restrict to real numbers, then we can actually give an elliptic representation, a geometric representation of the problem. So suppose that X is a diagonal matrix, and in that case consider the set EX, which is defined as the set of U such that UXU is 1. It's not hard to see that this actually corresponds to the equation of an ellipsoid, like the boundary, but I'm drawing it fill for the moment. And it's not also hard to see that this works for any matrix X which is strictly positive, because it just corresponds to a rotation of the ellipsoid. So then it means that an inequality of the form that I have written is basically just a statement about the containment of ellipsoids, and note that the containment gets flipped. Okay, so this is what we have. Suppose that we actually have a solution O, right? So that would mean that OV is mapped to W and the inequality is satisfied that I have written. Okay, so let us also suppose that the inequality is somehow saturated along one direction, and let that direction be along W. So that means that W is the point of contact. So we make two simple observations. We observe that the normal at V for the G ellipsoid and the normal at W for the H ellipsoid, they must be mapped to each other by the transformation O, right? This is easy to see. The normals have to coincide, otherwise there would be an intersection. Additionally, we can conclude that the ellipsoid H must be more curved along W than the ellipsoid V is curved along, the ellipsoid G. The curvature of the ellipsoid, okay, let me rephrase it, I'm sorry, I messed it up. So the curvature of the H ellipsoid along W has to be more than the curvature of the G ellipsoid along the point V, or along the direction V, okay? And this is kind of intuitive geometrically. It turns out that none of the assumptions we made were actually did lead to any loss of generality. So the condition that we can restrict to real numbers is something one can show. It's I'll not get into the details, but one can show this. The elliptic representation can also be shown to hold generally with the point of contact. One can show that the point of contact can always be made to work, and one can use Weingarten maps to evaluate the curvatures analytically. Readily, not analytically as well, but that's a different story. So now, given a k-dimensional problem, we start with tightening the problem so that there is contact along one direction. One can make sure that the contact is actually along the direction W, and then one can make the same two observations we made earlier, that the normals have to coincide and the inner ellipsoid has to be more curved than the outer ellipsoid. And using this, one can write a problem which has exactly the same form as the initial problem, but it has one less dimension. So it's a k minus 1 dimensional problem, and it again has all the properties of the initial problem. So we can repeat this procedure until we reach a trivial problem size like 1 or 2, and then we can solve it directly, and then we can combine all the different pieces to obtain the correct unitary. So this essentially means that we can convert any point game into an explicit protocol, in particular Motion's. and the limitation is, as I already mentioned, this is only numerical. So in summary then, using EMA or using the analytic solution, we can actually construct weak coin flipping protocols with vanishing bias, and numerically we can construct any point game into an explicit protocol. And this is essentially what I've written in my conclusion. So we found the exact solutions, and we found the numerical solution for the more general problem of converting any time-independent point game or a time-dependent point game into an explicit protocol. There's one little difference I wanted to mention, that the proof of the exact protocols does not rely on something called conic duality. This you would see if you look at the work in some more detail, while the result on numerical algorithms actually uses conic duality. The relevance is that conic duality makes the proof a little bit longer and a little bit harder. So the exact solution actually makes the proof smaller as well. So this was something I was very happy about. As I already mentioned, the original work is quite long, so any simplification in the proof is useful. There are a bunch of open questions. One of them is the resource requirement. So for instance, it was shown that the number of rounds that are needed for a weak coin flipping protocol with bias epsilon has to be at least exponential in 1 by square root of epsilon. So this means that as you approach zero bias, the number of rounds scales very rapidly. So this is not nice, but maybe the point games can be, we can find protocols that achieve, like for example 0.01 bias with a certain number of rounds. So this might be possible because that's an asymptotic result. Another issue is the number of qubits. So there's a very fascinating problem even now. So the best known protocol that we have for bias 1 by 6 use just I think 2 qubits and 1 qubit, while the best known explicit protocol for 1 by 10 bias, for example, uses has the number of qubits in that essentially tend to infinity as we tend to bias 1 by 10. So there's this discrepancy, and we don't know if this is sort of a threshold behavior or it's an artifact of just the construction. So there's that which needs to be investigated. Then there's the question of noise robustness. This is of course very interesting because in any realistic implementation there's going to be noise, and we would want to know how the noise affects the bias. Then there's this for me is perhaps the most interesting. It's the question of device independence. So this is for those of you who know, it's the setting where you don't even trust the device, and it's not clear whether or not coin flipping can be done perfectly in this setting. So we don't have the same kind of lower bounds that we have for the device dependent setting. So, and also explicit protocols, the best known is from 2011, and we don't know if there are better protocols. So in from both directions, it's a very interesting problem to study. So I think with this, I thank you for your attention, and I hope I've been clear. If you're interested in the subject, or if you're interested in learning more, please feel free to contact me. And yeah, thank you.